Hi everyone and welcome back to my channel A in Economist. So in the previous video on time series analysis, we have discussed what is a time series, what are the classification of time series and how a time series process looks like, right? So it was an introductory video on time series analysis. Now in this second lecture of time series analysis, we will go into the modeling of time series. Specifically, we will see two approaches. First is the classical approach and the second one is the stochastic approach of modeling any time series process that is given to you. So first in this video, let us start with the classical approach. What is the classical approach of modeling a time series? In classical approach, a time series yt can be broken down into four main components. So this approach says a time series has these four major components. Any time series process is composed of these four main components. What are those? First is the trend component. Trend component is also denoted as T suffix T. Then you have the seasonal component, which is ST. Then you have the cyclical component, which is CT. And then you have the irregular component or the random component, which is denoted as IT. Now, these first three components are also called the systematic components. They are the systematic components of time series because they can be estimated. These three components can be estimated exactly if you have the available data with you. But this fourth component, which is the irregular component or the random component, this is, as the name suggests, this is the random part. So any time series has two main parts, which is the first is the systematic part and the second is the random part. Now in systematic part, it has three main components, which is the trend component, the seasonal component and the cyclical component. And we will be going into each of these components in this video and we'll see how we can estimate them and how we can analyze them. So what you can see is that suppose you have a time series process as yt. So this time series process will be a function of the trend component, the seasonal component, the cyclical component and the irregular component. Now this, how these components will be there, it can be in the additive format, or it could be in the multiplicative format. They can be in the additive format or they can be in the multiplicative format. So I'm not writing it whole. I hope you understand. So this is not our concern. We can take an additive model or we can take a multiplicative model according to our need. But for now, you have to know that any time series process is made up of these four components. And here one thing to note here is that some of the components might be absent in some of the time series. So it's not mandatory that every time series has all these four components present. In some time series there might be only the trend component or only the seasonal component and so on, or it could be a combination of trend component, seasonal component or seasonal and cyclical component. So in this way the time series process can be made up of one or more components, right? Okay, now let us start with the trend component. What is a trend component? Trend is the long term upward or downward movement of a time series. So suppose this is t, here you measure the time period and here you measure the variable yt. So if your time series process looks like this, so it is only going upward and upward for all this time period. So you will say that there is an upward trend in the time series. Again, suppose this time series looks like this, so clearly it has a downward trend, and if it goes like this you will say that it has a constant trend. So this is what this definition is saying, that this is the long-term upward or downward movement of the time series due to the factors that influence the mean of the series. That we will see in a while. I have some examples for this. Some series may remain more or less at a constant level, right? So in this series, this is the mean is almost at a constant level. Now note that sudden or frequent changes are incompatible with the idea of trend. Trend may be thought of slowly changing non-random component of a time series. So this is what you can see in this diagram, that it is not fluctuating. So if the process is like this, suppose it goes upward, then it goes downward, then it is like this, then it is like this, and this. So here you cannot say that there is any clear trend available, right? Here you cannot say that any upward or downward trend is available, because after some time period it is either going upward or it is going downward. So there is no clear long-term movement of the time series. So in this diagram, no trend is available. But here, if for every time period it is either going upward or going downward or going at a moving at a constant rate, you will say that trend is present in the time series. So it is the slowly changing non-random component. There is no uncertainty, there is no randomness. That is what I have mentioned, that it is a systematic component. Trend is a systematic component, and you can clearly, measure the trend. You can estimate the trend, and we will see how to estimate this trend. I hope this concept is clear. Now let us see some of the examples of trend. As I have given you the example, so suppose this is the time series plot. If you plot time here and you plot YT here, YT is the quarterly earnings per share. Suppose this is the share price of Johnson and Johnson's quarterly earnings. So here you have the time periods available to you. In every 5 years, it is showing how the share price of Johnson and Johnson has changed over the years. And if find out the mean of this time series process, which I have given you here, suppose if you find a mean of this, it will come out to be in this format, A into T, where A is a positive thing. A is positive. Suppose expected value of YT, for example, is 2T. So if you, as you keep on increasing the value of T, so suppose T is 1960 here, so you will have some price. Then if you move to 1965, as the T value increases, the expected price of the share of Johnson and Johnson also increases, and that is seen in this following graph, right? So if you draw this estimated line, this is the estimated line, or the fitted line, or the regression line that we will talk about. You will see there is a clearly positive trend in the time series, right? So this is an example of the upward trend of the time series. Similarly, if you see this diagram, this is the time series plot of children's drowning rate between 1972 to 2004, and here you have the percentages, here you have the year, right? So if you plot this in a 2D plot, XY plane, so here you will see a clear downward trend, long-term downward movement is there in the time series process over the years. And this will be an example of downward trend. Mathematically, if you find out the process is YT and you estimate the average, you will see something like this BT, where B is strictly negative, and this will give you your downward sloping trend. And this is an example of a constant trend. So if you see this time series process, the over the years, the process is moving at a constant rate, or the trend is constant. It is not going abruptly upward or abruptly downward. It is almost at a constant level. So if you draw the mean line, it will be the estimated line. This will be something like this. It will be a straight line horizontal to the time axis, and the equation of the average will be something like this, where the C is a constant. This C is a constant, right? So this will be an example of constant trend. Now, the next important question that we will be answering is that how to estimate this trend. So we have understood what is a trend and what are the different types of trend possible. Now we'll see how we can estimate this trend. There are two approaches of doing this. There are two approaches of estimating a trend. First is a parametric method, or what we call method of curve fitting, or freehand curve fitting, right? Freehand curve fitting. And in this method, what we do, we assume a functional form for the trend component TP. In this method, we assume a functional form. We'll see in a while how we do this. And the second method is called the non-parametric approach, where what we do, we use a k-point moving average method of estimation. And now let us go into each of these methods one by one. First is the parametric method. As the name suggests, it will have some parameters that we need to estimate. The trend component will have some parameters that we need to estimate. So what we do, what I have mentioned here is that we assume a functional form. Let us see what could be the possible functional forms. The first and the most importantly used functional form is the linear function. First is the linear trend or the linear curve fitting. where you assume that this trend component takes a linear form a plus bt, as simple as that. So here you have two parameters. What are the parameters? A and b. You have two parameters, a and b, and your job is to estimate these parameters a and b. So you will get a cap and b cap. Once you know a cap, b cap, you can find out t cap, that is the estimated value of the trend. Now the second, functional form that is available, that is the quadratic. That is the quadratic functional form, where you have three parameters. It looks like this: a plus bt plus ct square. So you have three parameters and you want to estimate these three parameters, and that will give you your estimated trend. Or the third possibility is the exponential trend, where here you see there are two parameters and you want to estimate them, and here it is the example of a polynomial trend of pth degree. Polynomial trend of pth degree, here you have all these parameters a, b up to p, and you are trying to estimate all of them, right? So this is the method of parametric approach, where what you do, you firstly assume by looking at the graph. The first thing is that you need to plot this graph. Suppose you plot this graph, you have the time series data with you and you plot your graph like this. Now, do you think that linear trend will be a good fit for this? Actually, it's not. If you see, it is almost like a quadratic trend. So just by looking at this graph, you may think that, okay, I will use a quadratic trend. So I will assume my functional form of the trend to be like this: tt is a plus bt plus ct square. Or suppose you have this. So you'll say that, okay, yt is a constant thing. So yt is simply some constant c. Or yt is simply some at a constant level. So it has a linear trend. Or here you have a downward linear trend. Here it can be fitted using a linear trend. It will be a downward linear trend, and you assume this functional form, and then you try to estimate the parameter. So just by looking at this graph, you will have a knowledge that what will be a best functional form for your trend, and then mathematically you will estimate each of these functional forms to get the parameters values, and that will give you your exact trend. Now for giving you example, I have taken the example of a linear trend. Now I'll show you the steps how you can do this. Suppose you have this time series data available to you. Suppose your variable under concern is y, and you are measuring this variable over n periods. So you have y1, y2, y3 up to yn. So in a compact way, you can write in this way that yt, t from 1 to n. Or this is the same thing, right? So you have this data available to you. You have the data available to you. Suppose this is the population over the years. Population for a decade, or population for n decades, right? So this data is available to you. Now you assume a linear trend. I have taken this example of linear trend for simplicity. So t is simply a plus bt, and your job is to estimate a cap and b cap, the estimated value. Now what do you have to do? Simply you have to use the ordinary least square method of estimation. I hope many of you know this process, but just for clarity I am repeating. I have written everything. I'll be showing you the steps. So in ordinary least square method, what you do? You minimize the error sum of square. You minimize the sum of the error sum of square, right? So what you do? This is the expression that you want to minimize. Summation t from 1 to n yt minus the trend. So basically you are trying to minimize summation t from 1 to n yt minus tt whole square. This is the expression that you need to minimize. Now for that, what do? You need to find out the normal equations of this. You need to minimize this expression with respect to a and b. We minimize the error sum of square with respect to the parameters that we want to estimate, that is the value of a and b. So if you do that, the first order necessary condition is take the partial derivative of this expression and set it equals to 0, and this will give you your first normal equation. If you do this, this will give you your first normal equation. So I have written the steps one by one. So you are just taking the partial derivative of this with respect to a. So this 2 will come out here, you have this expression, and by chain rule you are again differentiating with respect to minus a, so it will be -1. Now if you know apply this summation over each of these terms, you will have this. And if you divide after you reach this step, you can pause the video, you can do it by yourself, you'll see how the steps goes. And in this step you are each side dividing each side by n. So if you take divided by n on both sides, you will get this. A is basically y bar minus b t bar, where what is y bar? Y bar is nothing but, okay, so y bar is what? Y bar is 1 by n summation t from 1 to n yt. And what is this t bar? T bar is 1 by n summation t from 1 to n t, right? This is the expression. So if you divide this side, both the sides by n, you will get this. A is y bar minus b t bar. Now your job is to find out this b, the estimated value of b, that is b cap. So for that you need to look at the second normal equation. Second normal equation. How will you do that? You will simply take the partial derivative of this expression with respect to b. If you do that, you will reach this point. Now here you have to substitute something. So a, the value of a we have already found out here, that is y bar minus b t bar. So you have to substitute here y bar minus b t bar, and for summation this you can replace n t bar. So let's see this expression. So t bar is 1 upon n summation t from 1 to n t. So what will be only this expression? This is n t bar, right? So you are multiplying this with this. So this is n t bar, and everything else is as it is. Now if you simplify further, you will reach this expression, where in the numerator you have this, in the denominator you have this. Now if you look carefully, what you will observe is that this is the expression of covariance. Covariance, if you know the formula, you will see that this is the covariance of yt and t, and here you will have a cap. Why this is a cap? Because this is the sample counterpart. This is the sample covariance, right? This is the sample covariance, and here you will have, in the denominator you will have variance of t, again the sample variance. This is also the sample variance, and see for sample variance, and for that you have to put this cap here, and if you estimate this value, you will get the beta cap. You will get the required value of the estimate of beta in the linear trend, right? So how will you find out beta cap? Simply find out covariance between yt and t, simply find out variance of t, and then just divide them, and this will give you your estimated value of beta. And what is the sample here? Sample implies this thing. Sample is this thing. So you have this data set available to you, and this is the sample on which we are working on, right? So we are deriving everything based on this sample, and that is the reason why this cap is necessary here. And once you estimate this, you will get the necessary value of beta cap. Now once you have beta cap, so you have this value, right? So beta cap is there, y bar you know, t bar you know. So you can simply find out a cap by y bar minus beta cap t bar. And in this way, you will have the estimated value of a cap and b cap. So I hope this process is clear to you. How do you estimate a linear trend? Simply, if you have this data set available to you, you can use the ordinary least square method, and you simply have to find out two normal equations that will be derived from the first order conditions of estimating the parameters of the model, and this will give you your estimated a cap and estimated b cap, right? A cap and b cap. And once you have a cap and b cap, t, what will be the trend? Trend will be a cap plus b cap t, right? So you know this value, you know this value. If you vary the time period one by one, you will have the estimated trend. And in this way, this is the first method or the parametric approach of trend estimation. As the name suggests, since we have estimated the parameters of the functional form of the trend, hence the name is parametric method. Now in general, you can, here I have taken a simplified example, but in general, if you want to estimate using a pth degree polynomial, what you have to do, you have to just change the functional form. So here the functional form is like this: a naught plus a1t plus a2t square plus apt to the power p, where this p is known. So this is the pth degree polynomial. P is a known integer, but the process will remain the same. Here also you have to minimize this yt minus tt whole square error sum of square with respect to all these parameters individually. So here you have estimated only these two parameters that are there in your model, right? But here you have p number of parameters. So you have a0, a1, a2 up to p. So basically p plus 1 parameters. A0 to ap is p plus 1 parameters. So you have to differentiate, take partial derivatives of this with respect to all these parameters, and that will give you your estimated coefficients or parameter values, right? A0 cap, a1 cap, ap cap. And now if you substitute them back into this, functional form, you will get the t cap, because t is known to you and you have already found out this estimated value. That will help you in deriving the trend. I hope this process is absolutely clear to you. And if you understood the process, I have given you a homework on this. Suppose you are having a time series this. So y1, y2 up to yn value is given to you, and you want to fit the model using exponential trend, right? Exponential trend. So here all you need to do, you have to find out the estimated value of alpha cap and beta cap using the least square method. So this is your homework. Please do this and let me know in the comment section what you get from here, what will be these values. And I have given you a hint also. All you need to do, firstly take the log, because that will make your calculations easy. And since log is a monotonic transformation of any sort of functional form, monotonic transformation does not alter your result, it will only simplify your calculation. So firstly take log and then apply the process as it is. So here you will minimize summation yt minus log tt, nothing else, right? T from 1 to n, this with respect to the parameters alpha and beta, and that will give you your expression. So please do this homework and let me know what you get, right? So with this we have finished the parametric method of estimation of trend. Now let us see the non-parametric approach. This is also a very simple method. Here we estimate the trend using a k-point moving average method. Now let's understand what is a k-point moving average. This is given by this expression tt cap. That is the estimated value of the trend. This is simply the average 1 by k. So you are using k point moving average. So you are taking average with respect to k. So 1 by k summation I from minus d to d by t plus I. Where this k is nothing but 2d plus 1. So here, if you have the available data yt plus 1, yt minus 1. So these data yt values are given to you if you have the lag values of yt. So these are the lag values. Yt, this is known to you. So if you know these lag values also, yt minus 2, so on and so forth, and also yt plus 1, yt plus 2. So these are the lag values of yt. So if you know this and if you take the average of these values over some time point, I is from minus d to plus d, we'll see how we can find this d value. If you take the average, so this is the moving average. So you are, suppose you want to know the trend at this period. So what you do, you consider some lag values of yt and you are taking the average of them. You are taking some lag values of yt and you are taking the average of them. That is known as the moving average. That is the moving average because you are taking the lag values, right? So you are not considering only the yt value but the lag values of yt also. And you are taking the k point moving average. So 1 by k, you are dividing it by k, and that will give you your estimated trend, where this k is 2d plus 1. And one important thing to note here is that the larger the value of k, the smoother will be your trend, right? So for example, suppose, let me draw here t and here you have yt. So if you use, suppose you use 3-point moving average, right? K value is 3, so you will have greater fluctuations. You will have greater fluctuations. Whereas if you use say 5-point moving average, your trend will be much smoother. So this will be your trend estimation using non-parametric method, and as you keep on moving, increasing this value of k, The larger the value of k, the smoother will be your trend. So this fluctuation, if you see in this diagram, this fluctuation is relatively less than what we see in the 3-point moving average, right? So this is what we have. Now let us see how we can find out the expression for 3-point moving average and 5-point moving average. So for 3-point moving average, the k value is 3, right? K value is 3, and now you know k is 2d plus 1. From the formula, k is 2d plus 1. Now if you put 3 here, it will be 3 equals to 2d plus 1, or 2d equals to 2, or the value of d is 1. So in this way you are able to find the value of d. Now what will be t cap? If you look at this formula once more, this is the formula. So you will have 1 by k. K is this I from minus d2 plus d. What is minus d? Minus d is minus 1. 2d is this, then y t plus I, right? So what you are saying here is that this will be y t minus 1 plus yt, because then you have 0 and then you have yt plus 1. So here how you are measuring the trend, or how you are estimating the trend, is that you are taking yt, the lagged values of yt, yt minus 1, 1 period lag value and 1 period forward value, right? Yt plus 1. Yt value, yt minus 1 value, yt plus 1 value, and then you are taking the average. You are adding these things up and then you are dividing it by 1/3, right? And this will give you your estimate 3-point moving average method, in the 3-point moving average method, right? I hope this process is clear. Similarly, you can do this for 5 periods. So k is 5 now. So 2d plus 1 is 5. So 2d is basically 4 and d value is basically 2. So what you will do here, simply t cap will be 1 by 5. I hope you got the process now. Y t plus I. So this is basically yt minus 2, yt minus 1, yt, yt plus 1 and yt plus 2, right? So in this way, so you are taking this lag values, yt value, yt plus 1 value, yt plus 2 value, and then taking the average of yt values in these 5 periods, and then this average will give you your estimated trend. And since you have not estimated any parameters in the model, right, you are just, you know, taking the average or the moving average of the value of yt. No parameter estimation is involved here, so you call this process as the non-parametric approach, right? Non-parametric approach, the name comes from the process that you are not estimating any parameters, but you are only, you know, finding out the k-point moving average in this method, and hence this process is called non-parametric method. And with this we have finished up our you know, trend estimation using both these methods, parametric method or curve fitting method and non-parametric method. And in the next video I'll be going into the seasonal component and the cyclical component and the irregular component, the rest of the parts of the classical approach, and we'll see how we can estimate those components also, right? So stay tuned for the next video, and if you haven't watched my first video on time series, please do that. I will give the link in the description, and then come back to this playlist again. And thank you for your time. And if you like this video, give me a thumbs up and do subscribe to my channel in Economist. And let's meet you in the next video. Thank you.